Hello, everyone. Welcome to the AI Agents Hackathon live streams.
The AI Agents Hackathon is a free virtual hackathon running from April 8th to April 30th.
We're hosting over 20 live streams where you'll learn how to build agents using various Microsoft technologies. At the end of the 3 weeks, submit your project for a chance to win fantastic prizes.
And now over to our friends at Reactor.
Hi, everyone. Thanks for joining us for the AI Agent Hack. Before we start, I do have some quick housekeeping. Please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is recorded. It will be available to view on demand within 24 to 48 hours. With that, I'd love to turn it over to our speakers for today. Thanks for joining.
Hey, good morning, good afternoon, good evening. Thank you for participating in the chat already. I see we've got some folks from Argentina, from London. So yes, I definitely have to do my worldwide hello. Thank you for tuning in to this presentation. Hopefully you will find it interesting and enlightening, something I've been working on for the last year or so. So what we're going to talk about today is real-time multi-agent LLM solutions. And I've built this solution over the course of the last year, kind of before this MCP stuff, before this A2A stuff. I was exploring this space. And so I've actually built it on top of a bunch of different technologies. And just in the last week or so, I managed to put it on top of MCP as well. So I'm using all of the latest things, and hopefully that will enable it to be super useful for you as well. You know, there are only 3 hard problems in computer science. There's cache invalidation, there's naming, and there's off by 1 errors. And so with that in mind, I took a bunch of time trying to figure out what to name my my creation, and I came up with YAP, yet another agentic protocol. And so with that in mind, I'm going to call this YAP throughout the presentation. But feel free to call it an agentic protocol, call it whatever you will. I've put it out on GitHub with a couple of different links here in the presentation. So just as an introduction, the yet another agent protocol is a protocol that enables dynamic addition and removal of experts to a multi-agent system. So this is the key, right? You have a multi-agent system, but how does that system evolve over time? How do you give it more expertise? How do you upgrade and extend that expertise without having to take down the whole system and bring it back up again? So what I kind of explored was the ability to add and remove agents kind of almost at runtime. And this allows you to evolve your system for your users just dynamically, however you will. So it's possible to add expertise to an existing system without having to redeploy the things you've already done. And it can give your users the experience of evolving knowledge as the chat is made smarter. You know, questions that they asked yesterday that weren't able to be answered are now able to be answered today because you've deployed a new expert or a new agent into your system. And so I started down this path by wondering, okay, we talk about multi-agents. What does it look like? What does it feel like to actually be in a multi-agent conversation? And in my head, it kind of evolved from the experience of a chat room. Like imagine I was in a chat room with a bunch of agents. That's kind of how I envisioned this going. And so I knew that I could build a chat room with a technology called SignalR that's able to be run out in Azure, and it kind of uses Websockets, but it has a hub. And so you can really quickly and easily build these chat room type experiences with SignalR. And so I started down the path of initially implementing with SignalR. And you can see the quick start on how to do a SignalR chat room of your own if you'd like to play just with that here in these slides. So I started on that, and then I thought, well, SignalR is very .NET specific. It has, kind of a bunch of little hops that get done in there. You've got a hub, you've got a server, and then you've got all your agents and clients that are logged in and chatting. So could I make it even simpler? Or could I use more well-formed technologies, more ubiquitous technologies? And so then I thought, okay, through the advice of some of my awesome colleagues, they said, well, what about gRPC? What about straight WebSockets instead of SignalR? And then finally, in the last couple of weeks, could I make it work in a MCP, Model Context Protocol type fashion? And so that's kind of the genesis of what I've built. And hopefully you'll find that useful and that'll resonate with you as well. So the basics of the protocol are actually pretty simple. You interact with what we call an orchestrator. I'm kind of on the fence about that name because it's been overloaded quite a bit here with multi-agent systems and agentic systems and even LLM orchestrators like LangChain and Semantic Kernel. But for now, we interact with an orchestrator with a chat entry endpoint that has LLM completions. So just like you ask for a completion from OpenAI, you ask for a completion from this orchestrator endpoint. But what's interesting about the protocol is that the orchestrator exposes a hello and a goodbye endpoints. And these are what are used by the experts, the agents, when they come online. So when an expert comes online, it says hello to the orchestrator. And when it leaves, it says goodbye. And just those two things being added into the system allows the orchestrator to do very interesting things as far as what it's able to send the LLM and the tools and functionality it's able to expose as part of a chat completion generative AI experience. Now, the implementations of the hello and the goodbye can vary quite a bit based on the underlying protocol. Like with SignalR, you've got a hub, a server, and you've got your clients. With gRPC, it's almost direct, just boom, 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 straight back and forth. With something like MCP, you've got your MCP server kind of in the middle. And then the orchestrator is basically an MCP client. So everything kind of varies, but the protocol and the idea has remained the same. And it's kind of stood the test of time as I've implemented it on top of these different transport layers. So if you know about generative AI, and you've probably seen a whole bunch of presentations already, one of the foundational things that OpenAI introduced with its LLMs was the concept of function calling. It can be a little bit of a misnomer. I actually don't like the name function calling because so many people get confused and they think that the LLM is actually calling the functions on its own and getting the data and interacting with the backend systems when that's actually not what happens. So what happens in function calling is you send a chat request, a prompt down to the LLM. And along with your prompt, a set of tools, a set of functions is also given to the LLM. Now, the LLM looks at your prompt, it looks at the set of tools that it was given, and it says, hey, one of those tools can actually help me out to get the answer to this prompt. And so what it will do is intermediately, without the user seeing this, it sends a request back to the caller and says, I want you to invoke this tool. And then I want you to give me the answer that that tool gave you. And so you, as the caller, as the developer, have to call the tool that you told it you have to get the answer back from that tool, and then you have to give that back to the LLM. And then the LLM puts all of that together and formulates its response back to the user, the actual completion. And so it's a little bit of a misnomer because the LLM isn't actually calling the function. You are as the developer. This is what Semantic Kernel and LangChain and all those other LLM orchestration frameworks kind of abstract away from you, is they will automatically call these functions in the background and work with the LLM back and forth before you even see the return value from the function. And so I kind of stood on those shoulders of those giants, and I implemented the YAP protocol by using function calling. And effectively what happens is when you say hello and when you say goodbye, you are adding tools into the list that's sent to the LLM, and you're removing tools from the list that's sent to the LLM. Now, the cool part is because LLMs are stateless, which means when you send one request to the LLM, it doesn't remember what the last thing that you said to it was. You have to consistently send it the history of the chat over time. And so adding and removing these tools over time is completely valid. And you can do this, and it doesn't hurt the experience of the LLM. It doesn't hurt the experience of the chat history. And it does actually allow the conversation to evolve. And so you can see kind of how this works together in the YAP protocol versus the OpenAI, traditional function calling. All we're really doing here is adding in the tools when the expert says hello. We add a new tool into the orchestrator, and then that set of tools from those experts is what's sent down to the LLM with each call. So that's kind of how it works. It's really simple in its idea, and it's really the only challenge is how to make it work in practice for whatever transport layer you're looking to work with. And so without further ado, I'd like to kind of demo the original genesis of this project, which was with SignalR, and then we'll step into the other transport layers as well, and I'll kind of go over the code and how everything works in each of these layers. So here we are in Visual Studio. I've got my SignalR project from YAP, and all I'm going to do is just fire it right up. And it's going to launch a whole bunch of windows you'll see here. And this will step through each of these here shortly. So I should also talk about kind of the idea that is at play throughout this entire demo. My son is actually a member of a robotics team here in Washington. And if you know anything about the first robotics competition, it's a worldwide competition. They actually just finished up their world championships here this past weekend. And it has, I think at world championships, there were 600 teams, but there's thousands of teams worldwide. Now there's an API over all of these teams, all of this team data, the events, the matches, the teams, their history, all of this stuff. And it's done through a website called the Blue Alliance. So you'll see TBA kind of sprinkled in here and there. And the Blue Alliance actually separates out their API, and it kind of lent very nicely to this idea of multiple agents. They separate their API based on districts, events, matches, and teams. And so I said, I'll create an agent over each of those chunks of their API. And so each agent then knows how to get information about, say, teams from the list of API endpoints for the teams in the Blue Alliance. And so what we'll see here is, I'll see if I can find it, the first one. So this is your SignalR hub. So this is the hub that connects out to the SignalR service in Azure. And you can see that as my agents came online, I have my orchestrator, then I have my teams expert, my matches expert, my events expert, my districts expert, and then of course my end user. And so the hub is basically just going to shuttle their negotiation requests back and forth to the SignalR service. If you're really curious about this, have a look at that quick start, get to understand SignalR a little bit better, and everything will kind of gel, and you'll see kind of why these pieces are needed. So we have the SignalR hub. The next thing that we have is the orchestrator. Now we talked about the orchestrator, right? The orchestrator is the one that I'm actually going to send my question to when I ask it a question. And then of course we have all of our experts. So we've got our matches, our events, our districts, and our a teams expert. Where was he at? Right here. So finally, we have the chat client. The chat client says, hey, welcome to the TBA chatbot. What would you like to know about first competitions, past or present? And so I'm going to ask it an interesting question. Now, the thing to know about this API is that, as you might imagine, every team is given a number. So the only way to query through the API is by team number, event ID, match ID, and district ID. And so if you ask it a question with a team name, it actually has to go find that team's number and then information about the team. So it has a two-step operation. So I'm going to tell it to tell me about team aerodynamics. This is why this query is interesting. Aerodynamics is a rookie team. And so if you remember about LLMs, they're trained on a point in time. And so their knowledge, the actual knowledge baked into the LLM, is actually static. It doesn't change over time. And so when you ask it about recent events, it can't answer those on its own. It has to go to some external source, get that answer, and then come back to you. And if you don't give it the ability to get to the external source, it'll either not answer you or completely hallucinate and give you an answer that it has completely made up. So I'm going to ask it about Team Aerodynamics. They are a brand new team. They're up here in Washington, and they are a rookie team just for this year. So it has to go out to the API in order to get this answer. Now, when I asked the question, you can see the orchestrator ran and immediately called over to the team's expert. The team's expert is now running search teams, and it will then talk to the Blue Alliance API, get the team data back, send that to the LLM, and then send it on back to the orchestrator. So we'll watch this at work here. So we got all the data from the API. We'll send it back to the orchestrator over here. And then we say, hey, they're known as Team 10079. They're out of Bothell, and they're a rookie team established in 2025. So right there, the orchestrator made the decision based on the agents that were logged in that it knew about. I need to call the Teams agent. The Teams agent then says, I can go get that answer for you, and comes back and says, here's the answer. The orchestrator says, that's good. That's the only answer I needed, and sends it right back to the user. So that's super awesome. But let's do something a little more interesting. Let's exercise this actual concept of multiple agents. So now I'm going to ask it a more interesting question. Now, it tends to hallucinate when I ask it this question, but it does illustrate the idea of what happens. I'm going to ask it, what events did Jack in the Bot, who is another team, they're actually the world champions, they just won this past weekend, and Bare Metal, that's the team that my son is on, what events did they compete in together in 2025? This is where it gets interesting. Remember what I told you about what it has to go and find for each team. It has to go get their IDs, and then it has to figure out what events they were all in, and then it has to figure out the intersection of those events. And so now the orchestrator actually has to orchestrate. It has to go and orchestrate, figure out which experts are going to have the answers and how to go get those answers. So let's watch it run. It takes a while. This is the other cool thing about SignalR, is that in the middle of running, I am able to send back status events all the way back up to the user. And so if you think about your experience with Microsoft Copilot, how it tells you, combing through documents that I found, looking for relevant web results. These are the types of information you can also send back as part of this protocol. It doesn't preclude that at all. So now we've searched for one team. We're going to search for the other team. It does take a while. These LLMs, I'm using GPT-4, so it's a larger, so it's a little bit slower LLM. Great. Now it's going to go to the matches expert, and it's searching for team matches by year. So this year, and then Bare Metal, this year, and then Jack in the Bot. Now it's going to say there are no events where they competed together. That's actually not correct, but you can see that if I go to my team's expert, it called here and got 2046, which is my son's team. And it also called and got, we should see one in here for Bare Metal as well. Yeah, it's got to be in here somewhere. It's the funnest part about working with these LLMs. See if we can find it. And then we go to the, the matches expert, and we'll see, look, matches says, it appears there are no events where these competed together. So the matches expert did get called. So that's great. It hit the orchestrator. The orchestrator picked up the information for the two teams, went to the matches expert, said, go find these matches, came back and gave us the answer. Working on prompts would give us the grounding that we need in order to make this not hallucinate. It would give us, all the types of features and functionality that we need in order to make this a little bit more accurate. But the general concept is here. You can see how the orchestrator kind of shuttled between the different agents to get the result. So let's talk about how SignalR actually worked in this case. The expert started up, or the whole system started up. And at first, the orchestrator said hi to the SignalR hub, and the user said hi to the SignalR hub. Then the expert said hi to the SignalR hub. And when the expert joined, the hub said, hey, SignalR service, go tell everybody who's logged in that I now have an expert here for teams, for matches, for districts. Go tell everybody. And so the SignalR service sends a broadcast event out saying this expert has joined. And so now the user can do things like, you now have the teams expert. The teams expert has entered the chat, something like that. And the same thing, the orchestrator, when it receives the expert joined event, it adds it to that tool list, like we talked about earlier. Then the completion, you can see it's a little bit convoluted. There's a lot of intermediate steps in here, but the idea, again, remains the same. The orchestrator asks the hub to go get the answer. The answer says, or the hub says, okay, I have to send that off to the orchestrator to get the answer. Goes and gets the answer. Now the orchestrator says, hey, LLM, figure out this answer to this question. Here are your experts. Gives it the tools. You can see that we ask it for a completion, and then give it a prompt and the tools. Now we have the tool loop where the LLM says, I need this tool, give me the answer. Okay, I need that tool, give me the answer. Okay, I need that tool, give me the answer. And this will repeat until the LLM thinks it has all the information that it needs. Once it has all the information it needs, it sends the final completion all the way back to the orchestrator. The orchestrator then bounces that back out to the end user, all through the SignalR service. And so then on shutdown, the kind of the opposite of that hello sequence happens, where the expert says, I'm going, goodbye. And now SignalR broadcasts out the event that an expert has left. And we can say things like, the Teams expert has left the chat. And the orchestrator removes the Teams expert from its collection of experts. And now if I were to ask it a question about a new team, it wouldn't be able to have the answer because that data wouldn't be in its training data, and it would have no way to go look it up. So how is it implemented? In the hello endpoint, this is kind of the meat and potatoes of this whole protocol, is the hello endpoint. How does the hello endpoint work? So this is C#, and so in the add expert function that gets called when that hello endpoint gets hit on the orchestrator, all we're doing is adding a new function into Semantic Kernel's function list. So we import a plugin that comes from a method, and in that method, we say, invoke on SignalR a get answer for this new expert that just joined. So the way that it looks is, I say, hi, my name is Brandon. A new function gets added into Semantic Kernel that says, if you need to call Brandon, you call him with SignalR, get answer, Brandon, and the prompt. And now we send that description of Brandon, his description that he gave, we send just those two things down to the LLM. The LLM will ask us if it needs that called. If the LLM says it needs that called, this function right here is what's actually executed by Semantic Kernel. So it asks SignalR to invoke something, gets the response back, and so on and so forth. So that's how everything works. Okay, what about another protocol? How does it look in something like gRPC that's wildly different from SignalR, but the same idea has to apply? So let's clean up our IDE here. Let's load up a gRPC version. And let's see what this looks like. The first thing you'll notice is that it's much simpler. There are two reasons for that. One, we don't need a hub and we don't have a SignalR server. The second reason is because I only implemented the Teams agent for my other protocols just to save on time and allow me to make sure that things do in fact work the way I want them to. And so what we'll see here is we see a Teams expert come online, introduces themselves. Let me zoom in here, introduces themselves and waits for a question. And then we see the orchestrator come online and they're waiting for a question, right? And so now I'm going to ask it that same question about team aerodynamics. And we'll see the orchestrator pick it up and send it immediately off to the Teams expert to get the answer. So now the Teams expert is running search teams, and we'll send it right back over gRPC to the orchestrator, who sends it right back over gRPC to the client. Bam. You also notice there, I do have streaming implemented. So when the responses come back, you can stream the responses still. So you're not locked out of streaming. Sometimes these multi-agent systems, they have so much stuff in the middle that it becomes really, really hard to take advantage of this streaming responses. With Yap, you don't have that problem because it's just these basic protocols and still just these basic ideas. Now let's play around a little bit with what I said about an expert leaving. I'm going to close the Teams agent, and it says right here, saying goodbye to the orchestrator. Now here's the orchestrator. Now it will not have the Teams agent on the inside. And so if I ask it again to tell me about aerodynamics, I don't have information. I don't have specific information about individual teams. Okay, and so now if I go back in here and I find my Teams agent and I start him back up, and now I ask about aerodynamics again, voila. The Teams agent is back online. The orchestrator knows about it, actively using it to go get the answer for the question that I'm asking. And so now imagine I asked a question about an event that we don't yet have an agent for, but I write the agent, then I deploy it, and the agent talks to the orchestrator adds it to the tools, and then I ask a question about the event, it knows how to go get that answer. So again, we got a great answer about team aerodynamics, this rookie team. So gRPC was a lot simpler. So what does it look like? I can fit the whole interaction sequence right on one screen. Hopefully you can read it, but the idea is very, very simple as it relates to LLMs and function calling and the Yap protocol. You simply say hello. The expert simply says hello directly to the orchestrator. It gets added into the tools, and then we ask the question. And when we ask the question, the orchestrator goes to the LLM, does the typical tool invocation that we're all familiar with, and then sends that response right back to the user. And then when we say goodbye, the opposite of hello, right? Say goodbye, we remove the expert from the orchestrator. And so now the system no longer has the knowledge that the expert was providing. And we saw that in action. And gRPC, again, the hello endpoint. What I'm doing in the orchestrator is I'm actually keeping a dictionary of all the experts who have said hello and their clients. So the client object that's created when the expert joins, I get the callback address for that gRPC endpoint. I store that in a dictionary indexed by the name of the expert that came online, and then we use those in Semantic Kernel. This obviously has issues if you were going to try to scale really heavily or work across multiple orchestrators. I would implement then something like a distributed cache that's shared between all of the orchestration endpoints. That's not hard in ASP.NET Core, so I didn't do that here for the sake of argument, but we'll see that in the future here in a little bit. But then again, same type of concept, same type of pattern. We import the plugin and we create a function that says, hey, for this name expert, for this description, this is the description of my expert. When you get a request from the LLM to talk to this expert, what you have to do is make this call. Look into my experts dictionary, call get answer async, and give it the prompt. And so again, you were just injecting this call out to the expert as part of a function call in Semantic Kernel. All right, let's see one more. Websockets is going to look a lot like gRPC, actually. It's very, very similar. We'll see just three windows get popped up here, and it'll do, we've got our orchestrator, we've got our team expert, and then we've got our client. And so I'm going to ask it about a different team. This team was actually a rookie last year. Tell me about Team Bagel Bites. And we'll see it go off to the teams expert and then come back to the orchestrator. Now, the point of me exercising kind of these different transport layers was strictly just to make sure that the idea that I had is actually ubiquitous enough to be, applied in many different ways in many different places. So it's proving itself out. I've used it in real projects. I've put this exact bot behind a Discord bot, and we use it through Discord for the robotics team. So it's really been a fun project to work on. So again, Team Bagel Bites, known as 9400, is a rookie team in 2024. So again, great response. Went and got the team's expert, came back, and did everything we expected. The interaction sequence looks a lot like gRPC. Simple introduction, then completion flow, and then the goodbye flow. The hello endpoint, a little bit different for WebSockets. We actually build up the whole URI to go back to the agent that came online. You can do this a couple of different ways. One way that you can do this is to have the agent give the orchestrator the pieces to formulate the URI, or you could just say, look, here's my URI. Go ahead and just call me right back here when you get this message. The reason I went with the former, where I give it the pieces, is because I actually pull out the remote IP address that made the call on line 9 here. You can see I look at the HTTP context and I grab that remote IP address of the expert that made the call into the orchestrator to say hello. So this allows me to be exact and correct. And then I just have the expert tell me if it's on a secured line. So is it WebSocket secured, WSS, or is it just normal WebSocket? And then what port are you on? We've hard-coded the /WS/agent route as just part of the protocol. You could change that, to whatever you want. Looking a little bit further down, again, same pattern. Create the function from the method, send a message and get the response over WebSocket when you need information from this expert. Now, last but not least, I want to show MCP. So MCP has been getting a whole lot of press lately. I recently read a blog that said you can't go to the grocery store without hearing about MCP. I think that's becoming high near true. So I said, okay, fine. Let's see what YAP looks like on top of MCP. It's a little bit difficult for me to zoom in on the Solution Explorer, so I'll just show it this way. So you can see in the Solution Explorer, I have an agent's MCP server. I also have my console app, and I also have my orchestrator. Now, in the context of MCP, all an MCP server does, the only purpose for existing, is just to expose tools out to whoever is using the MCP server. So now think about YAP. What YAP does is basically transforms an agent and its endpoint into a tool for usage by an LLM, right? So what did that mean? That meant that what I needed to have happen was the agents actually have to introduce themselves to the server with MCP. So the agent comes online, it calls an endpoint on the server that now adds it into the flow of what the server exposes as tools out to the clients for MCP. Okay, so when you spin up the MCP version of YAP, what you get is you get a Teams. Here's your MCP server. Zoom in. So you get your MCP server, and you get, hey, the Teams expert just connected, adding the Teams expert to the panel on the MCP server, right? And when we spin up the orchestrator is now an MCP client, right? And so the MCP client is spinning up and asking the MCP server for its list of tools. So here you can see that capabilities received, the tools list changed. So received a response for the method initialized. So we've initialized ourselves against the server. We send a request to get the tools list, and then we get back nothing. That's interesting. So then what happens? We say, oh, look, the tool list has changed because the Teams expert introduced themselves. Once the Teams expert introduced themselves to the MCP server, the server fired off the tools list change notification supported by the MCP protocol. Once it fires that off, all the MCP clients that are listening to that notification get it and can do what they want. So the tools list changed, the orchestrator says, and so it sent a request back. Okay, your tool list changed. What are the new tools? And once it got the new tools, it says, look, I got a Teams expert now in my tools list. Now that I have a Teams expert, I can go bake that into my semantic kernel calls that will be made when a user says, ask me a question about Teams. And so then finally, here's our Teams expert, where he looks exactly the same. He introduces himself and then asks a question or waits for a question to be asked. And so now we'll go back. We'll call our favorite example of team aerodynamics, and we'll watch all of this at work. And so you saw right away the MCP client got a request for tool call, and it immediately called the tool. That is the Teams expert. It gets an answer back and responds with the details about team aerodynamics. So that's how YAP works inside MCP. And you can see the MCP server here got the tools call, and then the client sent it to the server, and then the server sent it on to the expert. And that's how it all works together inside MCP. So the startup hello sequence sounds familiar at this point, but there's a little nuance here in MCP. You can see that the expert or the orchestrator registers with the server, and it says, hey, I'm here and I want to know about tool list changed events. So I'm going to register for those events. And then I'm going to ask you immediately for the tool list. Well, why do I do that? In case there were experts already online before the orchestrator came online. This way, if somebody beats me to the punch, I'll still get their tools back. And it comes back with an empty array at first, and it adds nobody to semantic kernel. Then the expert comes online and says hello to the server. The server then adds the expert to its internal list of tools. That's the only place that is used is to give back to clients. That's the only place that is used. It fires off the tools list changed events, which causes my orchestrator to ask for the tool list, get tools back, and add them into semantic kernel. Conversation flow looks almost identical to everything else, except for the fact that the orchestrator actually gets requests back to invoke tools and does that invocation on the MCP server. So it tells the MCP server to invoke the tool, and the server talks to all of its tools and gets the values back. Shut down goodbye, exactly the opposite. We say goodbye, the MCP server removes it from its cache, sends a tool list changed event. The orchestrator then asks for the tools and removes those experts from semantic kernel. So there's a little bit more code involved in the MCP side of things. When you create a server in MCP with ASP.NET Core, you say, I have an MCP server, line 8 here. You say, I have a list tools handler, and you tell it how it's supposed to get the list of tools. And so I have this list of connected experts on the server, and that's how I formulate the list back. Now, line 13 is a little bit interesting because what it does is effectively says, if you ask me for the list of tools, I'm going to subscribe you to tool list change notifications. You don't have to do that. It just made the most sense for this implementation that I've got today. And then, of course, when you build a server, you have to tell it when somebody asks for a tool to be called, what am I going to do? Well, I'm going to go to my connected experts that have said hello to me, and I'm going to invoke them. And that's it. On the hello endpoint, I decided to use, this is also another interesting piece with MCP. The transport between the expert and the MCP server can be whatever you want. In this example, I took my WebSockets sample and I converted it into MCP. So I'm still using WebSockets for the server to talk to the experts. That's okay. I could use gRPC, I could use SignalR, I could use any number of things. I chose to use WebSockets. So this code is all exactly the same, with the difference on lines 15 through 18. What we do on lines 15 through 18 is we actually create an MCP tool. These MCP tools then simply wrap anonymous methods, just like our semantic kernel invocations. And that's how the experts get invoked. So they get invoked over WebSockets exactly the same way as they did before, but they're exposed into the server as MCP tools. And when an agent comes online, I have to notify everybody, right? And so this is how I notify all of my clients. I send tools updated notifications. I go through all of my connected clients and I send them the notification method. That is, this comes from the MCP tool SDK or MCP SDK. I send them the tool list changed notification. And so then on the client side in the orchestrator, when I handle tool updates from the MCP server, I go back through all of the MCP tools that I've been given. I throw them all away because the tool list from the MCP server is idempotent. So it's the whole tool list every time you ask for it. There's no way to like filter it or ask for anything else today. People really want that feature, so I can see it coming in the near future. But today, we don't have a way to do that. So the way that I kind of faked this is I actually import the plugins from the MCP server with a prefix, MCP underscore. And so this allows me to go find all of the plugins that have MCP underscore, rip them all out, and then add in new ones that match up with what's on the server today. So that's how that works. So that's all I had for today. I know it was a lot. It's a lot of code. It's a lot of walkthroughs. But hopefully you could see that this YAP framework, the YAP protocol that I've kind of put together over the last year, before this rise of MCP, kind of as multi-agents were just kind of being talked about, it enables flexible, dynamic multi-agent implementations where you can add new agents at runtime and you can allow the system to evolve in real time. And you can communicate with these agents in very, very quick and direct ways. YAP is ubiquitous enough to be implemented in a number of ways. Today you saw SignalR, gRPC, WebSockets, and MCP. And I guess before I close, I have some time. I wanted to show kind of one example of just how ubiquitous this is. I'll do the gRPC one, but I have some scripts in the repo that will actually allow you to deploy any of the samples out to Docker as a Docker Compose resource. I should probably start up Docker really quick here. So right now it's building these in parallel in the background. Then it's going to build Docker images from each of them, just for the orchestrator and the Teams agent. And then it's going to start them up. And so now in my local Docker, you can see I have my YAP gRPC running. Where'd my Teams agent go? Let's try this one more time. There we go. Started. There we go. Now we got it. And it'll expose all the right ports and everything. And then I can just type launch client. And right now, this client is going to be talking to YAP inside Docker. And so if I look at all of the resources and I say, tell me about team aerodynamics, you can see it's going back and forth in between the Docker instance, between the orchestrator and the Teams agent. Now, the cool thing about this is that you'll notice back on my Docker Compose, there are no ports exposed by the Teams agent. It's actually talking internally inside Docker. This would allow this entire thing to be deployed and scaled exactly as you see fit. The other interesting thing you probably saw, kind of spoiled the surprise, but you can also deploy Kubernetes. So I'm gonna delete this deployment really quick so the ports don't conflict. And we will see. We'll see we've got a pod going here. That's the unchanged. Let me go back to my SignalR one. Not sure if I updated the Kubernetes deployment for gRPC yesterday. So we'll do the SignalR one. All right. Now let's see what we got. So now we have all of our Kubernetes deployment done here, and we can, get to all of that, and we can see that we've exposed the right ports. We can talk to them here. So running inside Kubernetes, we can talk to the exact same infrastructure that you saw working locally, that you saw working in Docker Compose. You can deploy it out to Kubernetes, works all the same, actually talks in between themselves. Everything's transported over the internal network as opposed to anything external. So it's super cool because now I can, I could take my pods and I could add more replicas, to any node, any pod, add more replicas and put that all behind a load balancer. And because LLMs are stateless, again, we get to use that to our advantage, and we could, run this as wide as we wanted and get it working that way. So hopefully that was interesting for you all. Hopefully you learned a little bit, and hopefully that's something that you can find useful, or if nothing else, maybe just in concept. But it was an idea that I've kind of been working on for a little over a year now. But thank you for attending. I appreciate it.
Hi, everyone. Hope you enjoyed today's session. If you aren't registered for the AI Agents Hackathon yet, register now at aka.ms/agentshack and start hacking on the agent of your dreams.
And if you have any questions along the way, just post in our GitHub discussion forum or attend our live office hours in Discord. And of course, make sure that you keep attending the live streams to keep learning about agents.
Once your project is ready, submit it before April 30th at 11:59 p.m. PT to be eligible for our prizes. Thanks for joining.